sparse distributed representations. It's been known for a long time that when you look in the brain, you find that at any point in time, most of the cells are relatively quiet, and a few of the cells are relatively active. It's sparse. That's what we mean by sparse. It's very few things are very active. Most things are quiet, and there's a lot of inhibition that's making this happen. It's been, Bruno Olshausen, I mentioned earlier, he wrote one of the seminal papers on sparse coding in the visual system, looking at it from an efficiency point of view. But only recently did I fully understand some of the attributes of sparse distributed representations, and we're going to talk about them. So everywhere you look in the brain, even coming out of the senses, you see sparse activity between regions, within regions. Everywhere you go, it's sparse. And this is not an accident. There are some properties of sparse representations which are essential for building intelligence, and I'm going to talk about them. So now I'm going to switch into a little bit more like a computer scientist mode of thinking here when we talk about sparse distributed representations. And I'm going to first tell you about how representations are formed in a computer, and then contrast that to sparse representations in the brain. So in a computer, we typically use something called dense representations. You might think of this, we have a few number of bits, maybe 8, like in a byte, or 128 bits, or 64 bits, something like that. We use all the combinations of 1s and 0s. So if I have 8 bits, I can use all from 0, 0, 0, 0, 0, 0, 0, into 1, 1, 1, 1, 1, 1, 1, 1, and everything in between, it's all valid. The individual bits don't mean anything. Here's start with an example, the ASCII code. ASCII code is an 8-bit code for letters, and so the letter M is represented by 0, 1, 1, 1, 0, 1, 1, 0, 1. However, if I say to you, what do those bits mean in an ASCII code? What does the third bit in that code mean something? It doesn't mean anything. It's just I have to look at the whole thing, and there's nothing about that representation which tells me what it is. There's nothing about those bits that say M. It's just an arbitrary assignment. The bits themselves have to be looked at as a group, and some programmer decided one time that that should be an M, and the computer knows nothing about that. Now, these representations are assigned. They're not learned. They're just made up in some sense, and that's a great way of working on computers. In the brain, we don't have that. We have sparse distributed representations. Let me just tell you what they are. First of all, you have thousands of bits. Now, when I say bits, you can think of cells, okay? So when I'm talking about bits, it's the same as cells. When I say there's a few active bits, I mean there's a few active cells. So I might have thousands of cells or thousands of bits. You need to have a large number. We typically work with 2,000 bits in my work at Numenta. And there are mostly zeros and a few ones. We will typically use 2% activation, so we'll have 41 bits and 1,960 zero bits. And so this is a sparse representation. I show you an example there, just showing a bunch of zeros going off to the distance here. Now, the difference here in the brain is that each bit has some sort of semantic meaning. Each bit has some meaning on its own. It's not like this is an arbitrary bit or an arbitrary cell. One moment it means this, and a moment it means something else. They have some sort of semantic meaning. We may not be able to figure that out very easily, but there's some sort of semantic meaning. And what we do is we pick the top bits, the top semantic meanings for a representation. And it'll become clearer. But let me give you an example. This is a made-up example for analogy. It's not the way we would do it. It's not the way it's done in the brain. But let's say I wanted to represent a letter like the letter M in a sparse distributed representation. I would come up with 2,000 attributes. I might have attributes for this is a vowel or this is a consonant. I might have attributes for where in the alphabet this letter is. I might have attributes for what it sounds like. Is it O sound or E sound? Is it a hard sound or a soft sound? Is it a fricative sound? I might have attributes how it's drawn. Is it drawn with descenders or ascenders? Is it a closed shape or an open shape, and so on. And then when I wanted to represent a letter, I would pick the 40 attributes that best represent that letter. And therefore, the meaning of the letter, the meaning of the thing is actually incorporated in the encoding itself. And that's a really great thing to start. Now, we're going to have to learn these meanings. The brain doesn't know these bit meanings, doesn't know what the cells represent when you're born. It has to learn them. But the basic idea is as I said. Now, there's some great properties that come with sparse distributed representations, and I'm going to go through those. This is pretty key to understanding everything else that's going on. Let's start with the simplest one. Let's say if I wanted to take two sparse distributed representations and say if they're similar. I could just basically line them up and say if they have similar bits, bits in the same locations, they have semantic similarity. If they don't, they're semantically different. And I can see, well, if I have 41 bits, I can be anywhere between no overlap and 40 bits overlap. But I can easily compare them, and wherever I have a 1 bit in common, it's semantically similar. The second thing is that what if I wanted to store one of these patterns and recognize it later? We're certainly going to want to do that in the brain. We want to say, oh, I've seen this before. What is it? How would I go about that? In a computer, we might save all 2,000 bits. But here, we're not going to do that. We're going to say, look, let's just save the locations of the 40 bits that are 1. And we would say, in the computer language, we would say we'd store the indices of the ones. So I'd have a list of 40 indices saying, OK, what locations are the 1 bits? And now if a new pattern comes in, I'll say, hey, do I have 1s in those same locations? If I find those 1s in the same location, I know I have the whole pattern. I don't have to look at all the bits. I only have to look at the ones that were 1 before and know where they are. That's going to work very well. But what if I came along to you and I said, OK, we have a problem. We can't store the location of all 40 bits, all 41 bits. We can only store 10 randomly. You can pick 10 randomly, but that's it. And so we now have 10 indices. We call this subsampling. And you say, well, will that work? If I see those 10, I have those 10 indices, a new pattern comes in, I say, is this the one I saw before? Is this the one I saved? And I'll go down and I say, look, the 10 ones in the right locations. And I say, that's good. And you might say, well, that's not good. I could be wrong. Maybe I got 10 of them right, but the other 30 are wrong. Well, that could happen. It's very, very unlikely to happen. But even if it did happen, what does it mean? It means I am now made a mistake, but the mistake is for something semantically similar to the thing I stored originally. Even though I didn't save all the bits correctly, and maybe a few of them are wrong, basically I have a very semantic similarity to the thing I stored before, and that's good enough. And we're going to take advantage of this, because these are actually going to be connections in the brain. We don't have to connect to everything. We only have to connect to a small number to be pretty certain we got the right pattern. Now, the final property here is one of union. Imagine I took 10 sparse distributed representations, 10 2,000-bit patterns, and I ordered them together. So wherever there's a bit, I add it up with a bit. So I have 10 of these guys. Each has 40 bits on, or 2% activity. And I create a new one, which is 2,000 bits, which has about 20% of the bits on. I just order them together. This is a one-way operation. I can't undo it. I can't say, oh, given this union, tell me what the individual bits were, individual patterns. I can't do that. But I can do something very interesting, almost as good. I can say, here's a new sparse distributed representation. Is it one of the original 10? So given the union and a new one, is it one of the original 10? And the answer is, I can do that. I can do it very reliably. All I have to do is say, are the ones in the new bit in the ones in the union? And if they are, then that's good. You might say, well, that could be an error. If you're following this, you might say, well, look, I could get maybe matching up one bit from one of those 10, and another bit from another of those 10, and so on. This is astronomically unlikely to happen. A little bit of math shows you that. And so this is a good thing. Why do we want to care about this? I said earlier the brain makes predictions. What the brain does is actually it's predicting lots of things all the time. It's not predicting one thing. It's predicting many things. And the way it makes the predictions, we're going to see, is it makes a sort of a union of predictions. And we want to know if something unexpected happens, we have to say, hey, what actually happened? Was one of the predictions, or was it not one of the predictions? So I can't always tell you what my predictions are, but I can tell you if this thing that happened wasn't correct. All right, so those are our properties. If you're going to forget everything else I talk about today and tomorrow, and you want to remember one thing from my talk, we can remember this, and I'll state this right very clearly, I'm certain of this, that all intelligent machines, biological or otherwise, are going to be based on sparse representations. These properties are critical, and they solve some very fundamental problems that have been bothering people for a long time.